Good afternoon, friends and students. Today session, which is related to design of connecting rod. It's a third session from topic design of IC engine components. Let us see how to design connecting rod. Now, learning objective of today's session. Know the design calculation of connecting rod. It consists of different parts. That is small end and big end of connecting rod. So what we have to do, we have to design connecting rod by buckling consideration, then find out the dimensions of cross section of connecting rod, then design big and small end and bolt for big end cap. Now let us see. Now here, first of all, we should know what do you mean by connecting rod. Already you studied these parts in thermodynamics also, but you will find it's a heavily stressed part in IC engine. And again, it is subjected to compressive force due to maximum gas load. Gas load means after expansion in IC engine or in cylinder, you will find the force exerted by the gas which comes on this connecting rod. And because of that, it is subjected to inertia forces. Again, second thing, this connecting rod is a slender engine component. Why name is used the slender engine component? Because here you will find while designing it, we are going to consider it as a column. And why it's as a column? When to consider it as a the long column or a short column. And already you might have studied that concept in design of machine element while designing the power screw. Whether buckling of the the body of that screw or a power screw which occurs or not. Again, here we have to decide is by using the slenderness ratio, that is L by K, that plays important role. And for that's why the name is given slender engine component. It is going to buckle. That's why while designing it, we have to take the care of buckling of this connecting. Before designing or considering it as a column to consider this buckling, we should know. Let us see its construction. Now here you will find the construction of connecting rod. Here this is the small end. This is the big end. This small end which is fitted here or connected to the piston part, and this big end which is fitted on the crank of the IC engine. Again here, the main purpose or main function of this connecting rod, it transmits the compressive forces. Again, when it transmits the compressive forces after expansion or combustion of fuel, when the gas force or the maximum gas load which comes on it, and because of that, the piston is fitted inside it, or you can say reciprocating motion gets converted into rotary as this big end is connected to the connecting rod. That means it is subjected to translational as well as the rotary motion also. Try to understand. And because of that, it is subjected to, or some stresses are going to induce in it. So while designing it, we have to take the care of that. Second thing, when it reciprocates, and after when it is subjected to maximum gas force or gas load, because of that, it is subjected to side thrust, which comes in again. We have to take the care of that side thrust also. And because of this, the reciprocating motion and rotary at the big end which connects to the crank. Because of that, the inertia forces uh, also going to act on it, and we have to take the care of that inertia forces also. Now let us see, before starting its design, so we have to consider as a this part as a slender engine component. Try to understand slender engine component. Why slender? Because length of this connecting rod is more than its width or the breadth or thickness, you can say. That's why it's a slender engine component. And if it's a slender engine component, that means it is assumed as a column, and we have to consider here the buckling of this column. Again here we know that how to consider this buckling of a column or this connecting rod. Again, there are two criteria. One is the Ehlers equation and second one is the Johnson equation. Again, when to go for a Johnson equation, when to go for a Euler's equation, that is also important. Again, you will find for a long column, the Euler's equation is preferred, and for short columns, again, Johnson equation is used or preferred. Again, based on the material used for the connecting rod, whether brittle material or whether ductile material, again, we can decide when to say it's as a column. So you will find when this breadth or the thickness, which is and length of the connecting rod, which is greater than the 6 times this. So you for a brittle material, then you can say that it's a column. And for a brittle material, it should be length or breadth. It should be greater than, or its length should be 8 times of that. Then and then you can say it's a column. Let us see. Again here, please give attention here. You will find cross section. Cross section means at this section you can cut at the AA or anywhere. You will find the cross section of the connecting rod. Generally, you will find rectangular, circular, elliptical, I section or H section. But this part is subjected to fluctuating load. Again, it reciprocates, and because of that, you will find generally I section and H sections are commonly preferred. And why these sections are preferred? Because having the high section modulus per unit area than the circular or other cross sections. So try to understand here, the I section or H sections are commonly used in case of connecting. Again, second thing, length of connecting rod depends on L by R ratio. For high-speed engine, this L by R, length of connecting rod, R is the crank radius when it's 4. High-speed engine, it is 4, and for low-speed engine, it is 5. This is also the another important, the relation that we have to use for high-speed engine and low-speed engine. Again, second thing, connecting rod is most heavily already, I have told, and subjected to fluctuating traces. That's why manufactured by drop foraging. Then, material used for the connecting rod, it's a medium carbon steel for industrial engine connecting rod, and alloy steel for aero engine or automobile. So you can remember medium carbon steel and alloy steel are the material which is used for the connecting. Now let us see buckling phenomena. What is happening here? Look at this. This is the connecting rod here. Two sections are shown. So this is small end, this is large end. And if you are going to see in the top view, again you will get this diagram. The A is the one front plane view, or you can say it's a top view, which is constructed here. And now here we have to consider the axis XX and the YY. Why it is to be considered? Because what we have to decide whether this connecting rod, which is strong along x-axis or along y-axis, because while calculating the value of I, that is mass moment of inertia along x-axis and y-axis, because which is required, and accordingly we can decide the section of the connecting rod. Now there are two planes. Let us see here. Buckling of connecting rod in plane of motion. Plane of motion means reciprocates. And here the small end, the piston pin is fitted here, the large end, the crank. You know that. The buckling of connecting rod in the plane of motion, the figure A indicates that. And plane perpendicular to the, perpendicular means towards this side, the in top you will get this perpendicular to the plane of motion. Now again here, what we have to do? We have to consider in this plane of motion, look at the diagram 1 or figure A. We will find ends of connecting rod hinge at crank pin and this is crank pin and this is the piston pin for buckling about x-axis. So here you will find when one single pin looking to this diagram in the plane of motion, the end fixity constant or coefficient, that is n is equal to 1 in this case directly. But you are going to refer this figure B, you will find plane perpendicular to the plane of motion. Here, the end, this fixity coefficient, you will find this side 1, 2, 3, and 4. That means for the second case, that is plane perpendicular to the plane of motion, so you will find end fixity coefficient are 4. Why this end fixity coefficient are important? Because we are going to prepare the Euler's equation of this buckling. Again here you will find connecting rod 4 times stronger. That means here only one end or end fixity coefficient 1, in this case 4. What does it mean? It means connecting rod which is 4 times stronger for buckling about YY axis as compared to buckling about XX axis. And how to decide it? It's okay from this, we are saying it, but we have to prove it. Look at this. Now consider this connecting rod is having a cross section that is I. Again, these are the standard, the dimensions or nomenclature which is used. You have to remember it. This is the thickness T. Again, width, that is B is equal to 4T. This is also the standard relation. B breadth is equal to 4T, and H again here, that is 5 times the T. So you have to use the standard cross section for the connecting rod. Again, as per the statement, along y-axis, it's 4 times stronger than the x-axis. That's why we can write 4 IY is equal to IXS. And therefore, I is equal to, again, mk square. You are studied that the radius of gyration. So we can write in this case, the 4k square yy is equal to kxx square. Again, therefore, kyy is equal to, or square is equal to 1 by 4 kxx. Again, what we have to do? We have to find out the area of this cross section. Again, we can easily find out 4t into this t, area of this. Again, this is t into, again, this t minus t means 3t. So here you can 5t minus 2t into this t. So you will get area of this middle part. And area of this section t into, again, this length means 4t. Again, 2 times 4t into t plus. Again, you can find out the area of this I section. So you will get 11t square for I, and always it remains same. No need to bother because these dimensions are fixed or standard one. Then find out Ixx. The 1 by 12 40 into pi to cube, Bt cube. Again, you will get this. Minus again along the x-axis, that means along y-axis. You are already studied in strength of machine element. The Ixx is equal to, you will get here 419 by 12 into t raised to 4. You can find out this. Again, in welded design also, in DME 1 also, we have studied this, how to find out Ixx and Iy. I don't want to go in detail again here. Then what you will get here area, then Ixx. Then we know the kyy square is equal to 1 by 4 kx square. The kx square is equal to Ixx by a. So we can find out kx is equal to 1.780. Now we have a value of kxx. Now here kyy. Again, we have to find out kyy. Again, find out the Iyy for this section and kyy like a xx. So after calculating Iyy here and kyy, you will get ky y square is equal to 0.992 square. Try to understand. Then what you will get? Find out the ratio Ixx by Iy. So you will get 3.2. And as per the our statement here, on the basis of end fixity coefficient, connecting rod 4 times stronger for buckling about y-axis. And it here, this analysis also satisfied the condition. So therefore, proportion of I section is satisfactory. Therefore, I section is preferred in connecting rod. Try to understand compared with other. And another one important thing I have already mentioned here, that is higher section modulus you will get in case of I section. It provides more strength than the other section. This is about the justification why I section. Try to understand. Then second thing, now I section is fixed. Now how to find out the cross section of this I section? That means we have to find out this dimension. For that purpose, we have to find out the forces acting on this connecting rod. Look at this diagram. Now here this is the piston, this is the connecting rod, this is the crank, and crank rotates here. Now we have to find out the dimension of this connecting rod or cross section, that is I here. Look at the arrow. Now again here you will find after expansion of the gas here in cylinder, this force P is the force P which is acting on the piston. Try to understand. And this force acting on the piston, which is because of the expansion, after expansion of the gases. Second here, side thrust. As I already explained in earlier session also, this connecting rod is subjected again in the piston because of this connecting rod or fluctuating load, side thrust load which is coming here. The PS, side thrust on the cylinder wall which is shown here, PS. Then PC. PC means force acting on the connecting rod along the axis of this connecting rod is the PC. That we have to find out. Then angle phi. Phi means this angle. Angle of inclination of connecting rod with this center line. With this center line. And theta is the angle of inclination of the crank from TDC, top dead center. Now again here look at the diagram here. This is PC and this force is P, and which makes an angle of phi. So we can find out here PC is equal to P upon cos phi. Try to understand. Look at this. This is PC, this force is P along this center line and this phi. So you will get PC is equal to P upon cos phi. But you will find when you will get the maximum force or gas load on the piston, when this PC, which is along the central line, but you will find here, when this angle phi, it is in the range of 3 to 3.33. That time you will get maximum load, which is coming on the connecting rod. So substitute this phi, which is equal to 3.3 or 3 degree. Then after substituting, you will find this cos pi becomes 1 or 0.998 or equivalent to 1. So you can put here it's equal to 1. So you will get PC is equal to P. That means force acting along the axis of this connecting rod, it should be equal to this force P. And this force P is nothing but a piston or the force acting on the piston. But this is because of the gas force or expansion of the gases. Try to understand. How to find out in earlier session also we have seen the force which is acting on the piston, that is PC is equal to area pi by 4 into d square, that is bore diameter, into P max. So therefore this P is equal to PC, which is equal to pi by 4 d square into P max, which is the force which is coming on this connecting rod. Try to understand. Let us see another here. Therefore force acting on the connecting rod, that is PC, we know that how it is coming, already explained from this diagram. Then second thing, what we have to do, critical buckling load, that is pre-critical, PCR. The PCR is equal to this PC into FOS. But here what we have to do, before using this expression, we should know the critical load which is coming. Again, as it's a slender component, we have to use the logic of buckling. Again, according to Rankine's formula, we know that PCR is equal to sigma C into A upon 1 plus A upon L plus KXS into bracket square, not A into bracket square. Why we are going to use, considering it as a long column, we are using this Rankine's formula here, where sigma C is the compressive yield stress, A is the cross-sectional area, A is the constant, depends on material, and its value is also taken here. I have written 1 upon 7 pi u 0, 0. L is the length of connecting rod and Kxx is the radius of gyration. I've already calculated in earlier analysis here Kxx. How much? 1.70. Area 11T. So we can substitute all these values here. So what we have to do? Find out critical load. So substitute all these values for critical load sigma C here. If it's made up of mild steel and plain carbon steel or connecting rod, sigma C 330 Newton per mm square. A is equal to 1 upon 7 pi 0, 0. So we can substitute all these values. One area A is equal to 11T square and Kxx 1.70. Substitute all these values. We will get P critical, and then P critical is equal to PC. So we will get this PC from this expression FOS. Now what you will get, this Kxx, then area, they are in terms of T. T means the dimension of this I section. Try to understand this T. Again, so by using this expression, PCR means this is equal to PC means this into FOS, and substituting A and KXS in terms of T, you will get this T thickness T. And once you know the T, we can easily find the B and H of the I section. B means this. Once you know the T, the B is equal to 4T and H means 5T. That means by using these forces which are coming on the connecting rod, we can easily find out the dimension of I section. Try to understand. Again, here second thing you will find, look at the diagram here. This connecting rod is having, the varying cross section. At the small end, small cross section. Again, here it is going to increase towards the big end. The varying cross section. That's why here the dimensions of this H, again, we have to vary. And where it is varied, look at this diagram here. I have written for small end, this H1 in the range of 0.75 H to 0.9 H. And for towards the big end, the cross section or eyes cross section varies. H2 in the range of 1.1 H to 1.25 H, and middle it's a 5 H is a standard one. That means by using this equation and relations of the forces and critical buckling load, by using this Rankine formula, we can find out the dimension of this I section. And again, how you have to vary from the small end to the large end. For that purpose, the relation of H is also given H1 and H2. We can use this to find out the dimension. Now let us see another. That means we can easily find out the dimensions of I section, and again is varying dimension from small end to the big end. Now let us see again here. In construction, I have already told here in first diagram, there is, it consists of the small end and large end. Again here in small end, this part is fitted in the piston pin or gudgeon pin. Again here inside it, there is a bearing means the small bush means cylindrical part, which is inserted inside the here connecting rod, and this bush which comes in contact with the piston pin and gudgeon pin. And look at the other end also. There is also the bush part here. This bush part is known as a bearing. But here this big end is divided into two parts or two halves you can say. And again this bottom part and the part of this connecting rod here, they are joined by using the nut and bolts. So here in design, what we have to do? We have to consider this small end, this large end or big end, then design these studs for the big end. And again this is the cap part, cap, because to fit it, because this big end is divided into two parts, it's a cap. That's why design of this cap also important one. Now let us say after calculating the dimension of connecting rod, now we have to see the small end bearings. Now here look at this, this is the small end, this part is the bush or a bearing. Again in the bush inside we will find the piston pin which is fitted here. Then again here, now this is the bush, or you can say the length of piston pin also, LP, bush, which is inserted. Now again second thing we will find here, the DP is the diameter of the bush or the piston pin also, and second LP is the bearing push. That we have to find out. How to find out? Again this bush, here piston pin is inserted. That means small end. Again the thickness of this bush, generally you have to assume it's a 3 mm. And it is designed by using bearing consideration. Bearing consideration means piston pin which is inserted in bearing bush. The projected area that we have to consider. The projected area, what you will get? DP and LP here. DP into LP. And bearing pressure, that is BP into P. So you will get this PC. Now let us see here. This is the, we have to design based on the bearing consideration. Bearing consideration means how to find out. Now the force which is coming on the piston due to gas, that we know that pi by 4 d square into P max, and the bearing pressure on this pin or piston pin or a bush. Bush is the bearing, that's why which remains same. Only area, this dP that we have to consider, dP into LP into bearing pressure. So we will get the force which is coming on the pin due to the gas. So we can compare here due to gas and due to here bearing pressure on the pin or the bush, dP into LP into BP. Compare this. So what you will get here? LP, this dimension, or even though you can find out the dP from this. Again, generally for this small end, allowable bearing pressure should be in the range of 10 to 12 megapascal. And second one, this LP by DP ratio in the range of 1.4. These are the standard one, this ratio. Accordingly, you can decide. Once you will get the LP or DP from, that means comparing this equation, you will get DP and LP. And bearing pressure 10 to 12 MPa. Similarly, we can easily find out the big end bushing or the bearing. So again, look at this. This is the big end. This is the crank pin. LC is the length of this pin and DC is the diameter. But in this case, you will find this big end is divided into half part, and there is a small gap. This gap is the crush. And why this gap is provided here? Because to have a proper setting of the bearing bush in the cap connecting rod. That's why this gap is provided of 0.05 mm, and it's press fitted when we are going to tightening the nut and bolts of the big end. This gap is known as the crush. Again, it is also designed based on the bearing consideration. Again, now here, what we have to do? The project. Again, here we have to find out this projected area. That means LC. Again, this diameter is the DC. Again, here you will get DC into LC is the area into this pressure. So you will get this force, and which is equal to again gas force which is coming on this connecting rod. And gas force means pi by 4 into d square into P max. Same. That means you have to use the same logic like a small end or big end also. Again, but in this case, LC by DC ratio in the range of 1.25 to 1.5. From this, you will get DC or LC. That means you will get the dimension of this bush or the bearing. Now let us see how to find out the dimensions of the bolt. Now here this the half part or a is known as a cap, or a bottom part is the cap. Okay, because large end is divided into two parts. Now again here are the position of the bolts and the PI max. PI max is the force which is coming here. Again you will find this force PI max is nothing but a maximum force which is coming on this cap or the bolts. And this force is nothing but a inertia force. And this inertia force is given m omega square into r into cos theta plus cos theta into n, where theta is the angle of inclination of the crank. But you will find how much is the mass which is coming on the large end. The mass which is coming on this the big end is equal to mass of the reciprocating part is equal to mass of the piston assembly. We have to consider whole mass of piston assembly plus 1/3 of mass of the connecting rod which comes on this big end cap. And then n is the L by R. L is the length of connecting rod, R is the crank radius, and is equal to L by 2. L is the length of strength. All relations already you studied here in earlier session also. So what we have to do, inertia force is maximum when this theta, that is angle of inclination of the crank, is 0. That means vertical position. And for the vertical position, you can substitute this value of theta is equal to 0. So you will get inertia force or maximum pressure or the force inertia force PI max is equal to this expression. Again, what is going to happen? This force PI max is shared by these two bolts, from this side one, from this side bolt. And this force area means pi by 4 into DC square. This is the core diameter of the bolt. And sigma T is the tensile forces in the bolt or for the material, allowable tensile stresses for bolt material. So we can compare PI max is equal to 2 times this, the bolt area into sigma T of the bolt material. And comparing this equation, this and this, what you will get here? DC. That is core diameter of the bolt. But we know the how to find out nominal diameter. The nominal diameter is equal to D is equal to DC upon 0.8. So you will get bolt diameter again. And again, second, what we have to do? We have to find out this TC means thickness of this cup cap. How to find out? Let us see. Again here, consider, assume this cap here as a freely supported beam. There is no support from this end, and uniformly distributed load centrally. This P max, PI max acts centrally. So we know that for a uniformly distributed load and the concentrated load, MB is equal to WL by 6. That is PI max into L by 6. And again, sigma B. How to find out sigma B? MBY by I. This is MB. And Y means TC by 2. Here, this TC by 2. And I, BT cube by 12. BC into TC by. You can substitute this value. You will get TC. So M by using sigma B is equal to MB means this expression. By Y means this. And I means this BTC cube by 12. So you will get what you will get? This thickness. This thickness means TC of the cap. In this way, we can easily find out the dimensions, bolt dimension, then cap dimensions, then I section of the connecting rod. Now there is one important point which is remaining, that is wiping stress. Because here the connecting rod is subjected to translational and rotational motion or rotary motion, and intermediate part of this connecting rod is subjected to elliptical orbits. And because of that, it is subjected to, because of this inertia force, the bending stresses are going to induce in connecting rod. And how to find out it? These bending stresses are calculated. Again, this inertia force m omega square into r. But you will find this bending stress, which is more at the L by 9 root 3 distance here. L by 9 root 3 distance from the piston pin. That means this is force F into R means L by 9 root 3, this distance which is from the small end or the piston pin. You will get the maximum bending moment. And again, we know the maximum bending moment sigma B is equal to MB by I. You can substitute this MB because of this inertia force, and where will get the maximum moment at a distance of L by 9 root 3. And now we know the IXS and this Y. Already we have calculated here during the IXX and IYY here. While substituting in IXX, IYY here. So we can substitute these values of IXX, IYY here directly in wiping stresses here. So you can substitute these values, so you will get MB max. So this maximum stress induced because of this inertia forces, translation of motion and rotary motion of the connecting rod is known as wiping stress. So what we have to do, we have to find out the stress induced in it. So in this way, we can find out dimensions of the connecting rod because of the inertia forces. We have to compare it with the gas or expansion forces, then small end bearing, then big end bearing, then diameters of the bolts which are used to feed this the divided part of the big end, and then curve thickness, that is TC, and the last one what we have to do, this wiping stress, this is because of translational motion and rotary motion of the crank. Rotary motion at the big end, translation motion because of reciprocating at the small end, and at intermediate points elliptical orbit. Because of that, maximum stress induced in the connecting rod at a distance of L by 9 root 3 from a piston pin. That distance we have to take, and again this is the